My name is Randall Fawcett, and today I'll be presenting toward a data-driven template model for quadrupedal locomotion. In this work, we are aiming to create a hierarchical control structure for quadrupedal locomotion, and more specifically, we first collect experiments using just the low-level controller to get locomotion data, and use that to create a data-driven state transition matrix. We then use the transition matrix to form a predictive controller that results in a desired center of mass trajectory and force trajectory. Now, both of these trajectories are then passed to a nonlinear low-level controller, which in turn produces torques that are sent to the robot. I want to briefly provide some background and motivation, and in particular, most state-of-the-art approaches for control and planning of quadrupeds use some form of a reduced order model. But the question becomes, what is the best model? And along the same lines, reduced order models may not contain sufficient information, and in some cases, traditional modeling techniques may even be intractable as systems become more sophisticated. Now finally, behavioral systems theory only applies theoretically to linear systems, which motivates the use here in the context of hierarchical control, since an approximate linear model can be used for planning while tracking is done with a nonlinear controller. Now, before beginning the derivation of the data-driven model, consider some linear time invariant system. Now, assume that you've collected input-output pairs denoted by UD and YD, and you use those data to construct Hankel matrices. Effectively, what this theorem states is that your new predicted values, U bar and Y bar, are trajectories of the LTI system if they're in the range space of the Hankel matrices that you constructed with data. In other words, future trajectories of a linear system under certain persistency of excitation criteria can be reconstructed using previously collected data. Now, for future use, we can decompose these matrices where the subscript P will denote the past portion used for estimation, and the subscript F will denote the future portion used for prediction. For some collected input-output sequence, we decompose that Hankel matrices into past and future portions, and the reason that we do so is to ensure that our future trajectory is consistent with our past trajectory. Namely, we have UINI and YINI that represent previous input-output pairs over the estimation horizon, and then the optimization problem must find this vector G such that it can reproduce the previous input-output pairs while also attempting to track future desired inputs and outputs. Now, this is subject to a defect variable sigma, which is only there for feasibility in the case of noise. This method's been used on various systems, but the G vector introduces a considerable number of decision variables, making the method intractable for our purpose. And we therefore opt to approximate G such that it can be removed as a decision variable. Now, in this work, we're drawing on the well-known single rigid body model, and we attempt to reconstruct a similar model using data. And in particular, we choose the inputs as the forces at the stance legs and the outputs as a subset of the center of mass states. We collect data on hardware by trotting the robot around on flat ground using only the low-level controller, and use this data to construct the Hankel matrices. However, as I mentioned, we want to remove the vector G from the problem, so we adopt an offline optimization problem to approximate it. Now, using this approximation, we can obtain the matrix denoted by script G, which is a data-driven state transition matrix over some prediction horizon. With that transition matrix in hand, we can now present a tractable predictive controller for use on quadrupeds. And in particular, our goal is still to track some desired inputs and outputs, but this time the controller is subject to the approximated model given by script G. Now, the removal of the vector G results in a significant reduction in decision variables, and we're able to run this in real time because of that. I want to begin by showing a few experiments that demonstrate the robustness of the method to unknown disturbances. So here, the figure on the right shows the evolution of the trajectory produced by the planner, which is stable even when subject to these intense disturbances. We also wanted to test the robustness of this technique against situations that were not captured during data collection. So nominally, we use a stance time of 200 milliseconds, which is the exact same as that which was used during the data collection for the model. But in these experiments, we use a stance time of 250 milliseconds for the top experiment and 160 milliseconds in the bottom experiment. We further examine the ability for the model to handle different gait parameters by using the exact same model, but for a walk gait instead. For both of these experiments, we're providing a time-varying trajectory produced by joystick commands. So this shows that we have the ability, A, to track time-varying trajectories, and B, to significantly alter gait parameters and still obtain robust results. Finally, we wanted to provide a brief comparison with a current state-of-the-art technique, namely the linearized single rigid body model. Now, the goal of these experiments was to have the robot track an elliptical trajectory, and as can be seen from both the videos as well as the plots off to the right, both of these methods perform similarly and are able to track the trajectory quite well. Lastly, I wanted to end with some videos of this algorithm being used outside to further show robustness in natural environments. Thanks for listening, and I'll open up to questions.